Hello everyone. In today's lecture, we will discuss how we can apply the concept of what we have done in the last lecture for the aircraft system. So here we are going to consider the longitudinal motion of the aircraft and how we can study the state transition matrix, eigenvalues, eigenvectors, and how we can analyze the system in open loop. So based on this, we can go through some control design techniques later. So this is a very important part before we move to the control design. So let's write the longitudinal motion of the aircraft. So before the equation, let's write the topics we'll cover in today's lecture. So first is we're gonna motion analysis of the longitudinal aircraft dynamics. And defined in state space form. State space form. And also we'll study analyze the system. Analyze the system based on state transition matrix. Eigenvalues, eigenvectors. So these are the components are very important before we move to the control design part. We need to study the system, how the system is going to behave. So here I'll write the equation, what we have obtained for in our classical control course. So here the parameter involved in the longitudinal motion, u, w, q, and theta. So let me write the equation what we have obtained. It's a very standard equation. U dot w dot q dot and system matrix. This is the example for this example actually. Lockheed Martin aircraft. Lockheed F-104 aircraft. So this data we can find from the side. So this is the values, the aerodynamic parameter stability derivatives we have taken for this particular aircraft, located 104 aircraft. So the system matrix obtained minus 0.0252, 0.1070, 0, minus 32.2, minus 0.2140, minus 0.44, and it is 3050, minus 0. Plus 0.00019, minus 0.0154, minus, and minus 0.4498, and this is 0, 0, 0, 1, 0, and the state vector here u, w, q, and theta. And our control matrix, D matrix, is obtained as 0, minus 2212, minus 4.650. And we are having two control input. This is control. This is, I can write UCT because also we are using U here in the state vector. So I can write UC. UC is the control. Okay. So this is basically I can write X dot. This is A matrix. This is X, this is B, and this is UC. Okay. So this is X dot equal to AX plus B. Now, this matrix you can easily derive if you are given the stability derivative parameters and aerodynamics parameters. So if you substitute the long in our the linearized model of the longitudinal motion of the aircraft, you can get this state space form. So now here, since the matrix is 4 cross 4 matrix, so doing everything analytically it's quite challenging. So what you can use the MATLAB code to get the eigenvalues and eigenvectors. So here, this is the MATLAB code. So here, if you notice here, this is our A matrix we have defined here. And there is a command. So if you use if you write sub E equal to EIC of it. So if you use this command, you'll get only the eigenvalues. But instead of this, if you use this command, it will give the eigenvector, basically the P matrix. Here we can write, instead of P, we can write, this is T matrix, and this is our diagonal matrix. So the diagonal matrix is nothing but, D is nothing but here, you can write, this is basically T inverse T. This is basically the diagonal matrix. And here V actually, our transformation matrix, which is our, since there are, the system dimension is 4 cross 4. So we'll have 4 vectors, V2, V3, and V4. So this is basically the eigenvectors which form the V matrix here. Okay. So this is how we can find, this is, I can write, this is the P matrix. I can write, this is the P matrix, and this is the D matrix, which is nothing but T inverse T, diagonal matrix. So if you notice, we have only the diagonal terms in our system. The off-diagonal terms are 0 here. Okay, so here we're gonna do some analysis here. Since we are having, if you notice what you have done previously, we denote this matrix. Also, we denote as A. Also, we have noticed this. Also, we denote A dash, right? This is also same thing what we have done in the previous lecture. So now, here we can write, let me rewrite this A dash. Change the color. So here A dash I can write minus 0.4459 plus 2.1676i. I can put here 0, 0, 0. Because the off-diagonal terms are here. If you notice here, it's 0 actually. Off-diagonal terms are all 0 here. Okay. And the second row, 0 minus 0.4459 minus 2.1676i, 0, and 0. This is 0, 0. And our third term minus 0.01766 plus 0.147 for I. Zero, 0, and 0. This is, we can write it 0, 0, 0. And last term, we are having minus 0.0166 plus minus, because these are the complex conjugate root, 0.147 for I. So this is our, the system is written in off-diagonal terms. So what we have done in the previous lecture. So we can assume the system is written as in different domain, z of t, a dash, z dot of t, and like that. So this is our new system. So here, a dash actually this matrix. Okay. So now, if you will start with a system based on the diagonal elements here, the diagonal elements, what we have done, this diagonal elements. So if you notice, there are two complex conjugate roots. One, this is complex conjugate, one pair, and this is another pair, complex conjugate. So if you notice here, in this case, if you remember in our last lecture course, this talks about the damping part, this talks about the natural frequency. This is also damping, this is also frequency. And in this complex conjugate roots, this is the damping ratio and this is the frequency. Similarly, this for this case as well. So what you get here? So here, in this complex conjugate root, since the frequency is higher, the period will be less. And in this complex root, the frequency is lower than this frequency, automatically the period will be high. Why? Because how to find the period? T equal to, we know, T, this is the period, period, 2 pi by omega. So omega, if it is high, the automatically period will be less. If it is omega goes to low value, the period will be less. So in this case, so easily you can comment, this is this part, this complex conjugate root yields the long period motion or phugoid motion, and these complex conjugate roots yield the short period motion, because in this case, the period is less compared to this roots. So we'll go through detail about it. So now, let's talk the short period root, how it is coming, short period case. Short period. So here we have the complex conjugate root. So here minus 0.4459 plus minus 2.1676i. So since the roots are, there are two roots, so we can compare this system with our previously derived case. So we can write in a standard system, TS, some transfer function. We can write omega n square divided by s square plus 2 zeta omega ns plus omega n square, right? So if you, and for this case also we'll have some second order system for this case. In this case also we'll have some second order equation. So if you compare both the cases, so we can write here zeta 1, 2, also we can write in terms of natural frequency and damping ratio in the structure, zeta omega n plus minus I omega n divided by 1 minus zeta square, right? So here, zeta is the damping ratio, and this is natural frequency. And this whole term also we can write as damped natural frequency. Not damped, sorry, not natural, it is the damped frequency. You can define damped frequency. Why damped frequency? Because damping factor also there in the function omega n over 1 minus zeta square. So now this is also we can write in the structure minus zeta omega n plus minus I omega d. Omega d actually omega n 1 minus zeta square is the damped frequency. Now, if you compare this equation, this equation and this equation, so because this is the roots, these are the roots we are getting from this characteristic equation, and this is the roots we are getting from our aircraft system. So, and this is the roots we are getting from the standard transfer function. This is the standard transfer function, right? So now we can compare this result with this result, and if you compare both the result, we can write zeta omega n equal to 0.4459 and omega n 1 minus zeta square equal to 2.1676. And from this, we get zeta equal to, we can write zeta equal to 0.2014 and omega n equal to, we can find 2.214. Okay, so this is the case we are getting for the short period case. So this whole things for short period case. Now, for the long period case or Fugit case, similarly, if you compare for the Fugit mode or long period case, we can write 1, 2. So there are two complex conjugate roots, which are basically minus 0.0166 plus minus I 0.1474I. Okay. Similarly, in this case, if you do the same analysis, we can write the standard roots from the standard transfer function, this structure. So if you compare this function, so these roots with these roots, we can find zeta equal to, we can write 0.11 and omega n equal to 0.14. So the thing is, if you notice carefully, short period case, it is obviously from the calculation, it's quite clear that this is the value for the omega n for the short period case, because 2.214 is the frequency, natural frequency. Now, if you find p equal to 2 pi by omega, this is the omega, if you fit here, we'll get some numerical values. And in this case also, if you find the t 2 pi by omega, so the value is, what will you get? Something A and B. So A is less than B. So that's why, so you can say it should be So period is less in short period case. Also, if you look the damping part, here the damping ratio is higher than the damping ratio what you get in the long period case. So if in the system, if it is high damping, we can diminish the sustained oscillation very quickly. This is this is very important way how we can analyze the motion dynamics, natural motion dynamics of the longitudinal motion of the aircraft. So I hope it is clear this part, how we can define or how we can come up the conclusion whether the system is how it is stable, whether taking more time to get stable. Because anyways, the roots are all lies in the negative side. I mean, right hand side of the S-plane. If you see in the particular example, we are having all the roots in the left hand side. So it means the system is already stable, but how they are going to behave over time. So there are two important part in this particular motion dynamics on the short period and long period, and how we can discuss from the state transition matrix. So this is our state transition matrix. State transition matrix also we can find. Sorry, actually this is the this is basically the system in the diagonal form, and how we can use the system which is in diagonalized form. We can use this matrix, and we can do the analysis, short period case and long period case. So this is how we can analyze the system. Now we'll move to the next part, which is basically one of the most important concept in control theory, controllability. Controllability is a very important part. Why? Before you go to the design of controller, we need to check whether the system is controllable or not. For example, we are having space, for example, and we have multiple states in the system, x1, x2, xn, or we have the system in this form, x dot equal to x plus bu. And let's assume this x actually there are a lot of states, xn states are there. Now you are applying the control input to this system u of t. So controllability means if all the states affected by this control input, then we can say the system is controllable. If any of the state is not affected by the control input, then you can say the system is not controllable. So let's take a motivation example, then it will be clear. Let's take an example. So we have system x dot equal to -2, 0, 0 and -1. And we have the state vector plus we have the control matrix 2, 0 and u. Okay. And we have the output equation equal to 3, 0 and x. So here basically x actually x1, x2, two states are there, x2, x1, x2. Okay. Now it is by looking at this system, it is quite obvious in the second order system, the matrix is 2 into 2. So now we'll find the transfer function here. So in this particular case, since the matrix is 2 into 2 dimensional, we may get, as per the theory we have done, if the system is 2 cross 2 matrix, the characteristic equation will be of second order. The characteristic equation of the system should be second order. But let's check whether the characteristic equation is coming out to be second order or not. So before that, we'll go to the how to find the transfer function for this in the state space model. So the state space model, we know x dot equal to x plus bu and y equal to cx. Du part we are not considering here because we are not using any feed through case. Okay. If there is any feed through, it means if there is any control from the reference signal, then du part should be there, but it is not there. So du part we are having to be 0. So now we'll take the Laplace transform of this equation. We'll get S xs equal to axs plus bus. Okay. And y is equal to cxs. Okay. So one thing, please remember, to find the transfer function of the system, initial condition assume to be zero. If you assume non-zero initial condition, so we can't apply the principle of superposition and system will be nonlinear. So for finding the transfer function, the system should be, it's a system should have initial condition should have zero. This is the condition. So now from this we can write Si minus A xs, right? And transfer function concept we know, output y of s by input, right? So from this, we'll substitute this ys, or no, this xs term, what you are getting here, this xs term, we'll substitute here. So what we'll get, if we substitute, so we'll get Si minus A, we can write OIS divided by C equal to BUS, right? And from this we can write, I can erase this part. So from this we can write OIS divided by US equal to C into Si minus A inverse B. So this is the transfer function. If you use the state space form, we can get this transfer function here. Okay. So now we'll use this method, how we can find the transfer function for this particular example. Okay. So let's work. So y is divided by US, we can write CSI minus A inverse B. And we can substitute the parameters, values of the matrices. Actually, there's a typo. Actually, the system, the output matrix, C matrix, it should be 2. Okay, 3, 2. So y is function of all the states, x1, x2. So now we can write 3, 2. We have the system SI is 0, 0 is, we can write minus 2, 0, 0, minus 1, and it is inverse. And we have the control matrix 2, 0, right? And from this we can write 3, 2, 3, 2, and we can take this part. If you solve this part, if I solve the inverse of this matrix, we get 1 upon s squared plus 3s plus 2, and the matrix s plus 1, 0, 0, s plus 2. Okay. And we have the control matrix 2, 0. And from this, we can further write 1 upon s squared plus 3s plus 2 and 3, 2. And we have if you multiply these two matrices, matrix and vector, we get this 2s plus 2 and 0. And from this, if you solve all this stuff, we'll get 6s plus 6 divided by s plus 1, s plus 2. So we are getting finally 6 upon s plus 2. Oh, the problem. So what is the problem here? The problem is, as you said, the characteristic equation of the transfer function ys by us. So we'll have some expression like numerator a of s and denominator of s. So we're supposed to get the denominator part actually the characteristic equation. We're supposed to get the second order, but here we are getting first order equation. But why this? So it means there is one state is not controllable. So if the order is not 2, the rank is not 4. So there is one problem. The system is not controllable. So let's look how it is happening. Let's do the observation. So now if you extend, if you split this equation, if you split our system equation, let me define this equation number 1. If you split the equation number 1, we'll get x1 of dot x1 dot equal to minus 2x1 plus 2u, right? And x2 dot equal to minus x2. Oh, so if you notice here, this system does not affected by the control input u, because this u is going to affect the x1, and there is no direct link x2 and x1. So the x2 is completely decoupled from the first equation. So that's why this equation, we can say this equation does not affect it by the control input. This is a very, very important takeaway. So now if you want to get affected x2 dynamics, so we need to modify x2. So if you had something instead of this one, if you have, for example, system x2 dot equal to minus x2 plus x1, then the system is controllable, because here x1 is affected by u, and this x1 is going to affect x2. So that's why this system, whole system not controllable, because x2 dynamics is decoupled from the control. So this is how we can do the validation whether the system is controllable or not. So there is a direct rule we can test the system, because if you are asked to do the controllability analysis for a big system like the one we had this aircraft system, this is quite difficult because we have to do a lot of analysis. So there is a direct rule we can use how to test. So a linear system, let me write a linear system described by x dot equal to ax plus bu is controllable if and only if the contributing matrix, which is P, we are defining P, and what we can form using the B and A matrices. B, AB, A square B, dot dot dot, A minus 1B is rank A. So it means if you assume here the A matrix, which is n cross n square matrix, and if the rank of this matrix is also 1, then we can say the system is controllable. There is another way also you can test. If determinant of A matrix is not equal to 0. That is also another way. So this is the way generally in control synthesis we do this criteria. Yes. If the rank of this matrix is full n, then we can say system is controllable. Yeah. So let's stop it here. In the next lecture, we'll continue. We'll take an example on how we can test the controllability of the system. And we'll also study how we'll start the control part. This is the main part in this course, how we can design the controller for a particular system once the system is fully controllable. Thank you.